When talking about the mass spectrum of boron, and even going back to applying Avogadro's number to calculations, we were using the average atomic mass. Average atomic mass, in its name, means that we're talking about the weighted average of all of the naturally occurring atoms of that element sample. So sometimes it's just called atomic mass, not average. Sometimes it's just called the mass. Sometimes it's called molar mass. This is different than mass number. So once again, mass number would be a whole number. That's protons plus neutrons. If we're talking about just one isotope, we could know protons and neutrons to find mass number, or mass number and protons to find the neutrons. But normally we're not talking about just one atom or one isotope. We're talking about a sample. And even when we have a tiny, tiny sample, just maybe even 1 gram of something, that contains billions upon billions of atoms. And if that element has more than one isotope, it'll have a mixture of all of those isotopes. We don't want to represent just one isotope or another. We want to show, on average, what is the weight of that sample. That is the average atomic mass. It's a weighted average that accounts for the mass of each isotope and its natural abundance. Often, we are given mass numbers of the isotopes, and we do the math with that. But really, those isotopes have a mass that is slightly different than the mass number. In general, protons and neutrons are dealt with as if they have a mass of 1 AMU, but each one's slightly different. We have electrons in there as well, and there's also a concept called mass defect that all of that kind of piles up on here to make a sample of an isotope actual mass not exactly equal to its mass number. We don't need to know the explanation or theory behind any of that. Just that don't be surprised if you are told that a isotope of maybe gallium 68 doesn't have a mass of exactly 68.000. It's going to be very, very close to 68. More important than that, though, the average atomic mass gives us a picture of maybe what is the most common isotope or which isotopes are more common than others. With boron and 2 isotopes, it's fairly simple to see which one's more and less abundant. With a more complex sample, not even down here, but still a single element, zirconium, we've got a whole mix of isotopes that comes out to an average of 91.2. Many of the isotopes are lighter in the 90 to 92 range, but we do have some heavier ones. And with the weighted average, accounting for the weight of all 5 occurring isotopes, but also their abundance, we get on average an atom of zirconium would have a mass of 91.22, or more applicable to us, if we had that full mole, the 6.02 times 10 to the 23rd atoms of that isotope, then it would weigh out, based upon the mixture of all those different isotopes, to 91.22 grams per mole. So when we're looking at mass spectra down here, and I talked about gallium here, we are looking at a weighted average, and we're using our graphs to find out about that weighted average.